Okay, welcome to the final talk of the second day of this conference. It's a great pleasure to introduce Professor Fred Diamond from King's College London, who will give his second talk on Sayre weights for GL2 over totally real fields.
Thanks for the introduction. And following Rudy's suggestion yesterday, I'll take questions at the beginning. But first, let me give a quick recap of the first talk. So the overall plan is to first review the weight part of Sayre's conjecture over Q, and I am actually stating three versions. There's the original recipe for Sayre's weight K, and then more algebraic version in terms of Sayre weights. The idea being that these two variants that I'm describing generalize well to the Hilbert modular setting, the setting of GL2 over a totally real field. So as I was saying, there's firstly the algebraic variant in terms of Sayre weights. And then I was just starting at the end of the first lecture to talk about Edixhoven's variant in terms of geometrically defined mod P modular forms. And so first of all, Sayre's recipe for low weights, so for weights between 2 and p plus 1, can be made very explicit in terms of the local Galois representation. And more specifically in terms of the restriction to inertia at p. In the reducible case, it's an extension of trivial by cyclotomic to the k minus 1. And in the case of an irreducible representation, an irreducible local Galois representation, the restriction to inertia being the sum of the correct powers of a fundamental character of Niveau2. And then the algebraic version in terms of Sayre weights, where by Sayre weights, I mean irreducible mod P representations of the finite group GL2 of Fp, which can be described explicitly in this way as tensor products of powers of the determinant, so twists by the determinant with small symmetric powers, so between 0 and p minus 1. And then there's a natural notion of what it means to be modular of such a weight if the corresponding Hecke eigensystem occurs in the cohomology of the modular curve in characteristic P with coefficients in a representation, well, coefficients in this representation. And then you can state, let's see, is there anything here I wanted to, oh, and this description somehow, or this formulation somehow captures the original formulation because rho is modular of some weight k if and only if it's modular of some weight which is a Jordan-Holder factor of the k minus second symmetric power. And then in this language, the conjecture, the Sayre weight conjecture becomes that, and in using p-adic-Hodge theory, the Sayre weight conjecture becomes that rho is modular of some weight if and only if it's the reduction of a crystalline representation with the corresponding Hodge-Tate weights. And of course, over Q, these are theorems. And I was just starting to discuss I was about to discuss the geometric variant. And so now, as promised, let me see if there are questions.
I suppose the participants can unmute themselves to ask questions. I'm not sure what the settings are.
Maybe just a comment to that last, the equivalence being of actual numerical weight k and being Serre-Waite sigma, one of the Jordan-Holger factors of the k minus 2 with symmetric power. That seems really remarkable because there's so many, as k is large, there's so many sigmas, Jordan-Holger factors, and somehow any one of them sees the weight k. So
Right. So when k is large, yeah, that's a good comment, because when k is large, as long as k is in the right congruence class mod p minus 1, all possible Jordan-Holder factors will appear with the correct central character, and so the representation will be modular of that weight. And in fact, something I didn't say explicitly, but should have, is that in Serre's original recipe, the value of k of rho is bounded by p squared. It's something on the order of p squared. I forget the exact formula. And once you get beyond sim p squared plus or minus whatever, the reduction of the symmetric power contains all irreducible representations with the correct central character. And maybe I should say the same is true for level structure at P. You see that, or for types, once your type is sufficiently ramified, once the conductor is high enough, the reduction of the type contains all the Jordan-Holder factors with the correct central character. In fact, I think conductor p squared, isn't it? Okay, other questions?
Yeah, I had one question. Yeah, so in that other equivalent formulation where you're talking about existence of crystalline lifts, the theorem which says that we are using Berger-Lizou and Fontaine-Lafayette theory. So, I mean, yeah.
Yes.
Yeah, so I mean, we need to construct crystalline lifts, right? Here, I mean, for rho g qp to show that the original set of weights is same as this set of weights, right?
So maybe it's indirect that one knows that there are crystalline lifts.
Okay.
Right. So to see this equivalence, one needs to invoke the Clay-Mazar conjecture.
I see.
Which implies that so that implies that if sim k minus 2 has sigma mn as a Jordan-Holder factor, and sigma mn is, there's a better way to state this probably. So here's a better way. So the reductions of crystalline representations with Hodge-Tate weights 0 and k minus 1 are precisely the local Galois representations whose Serre weights include Jordan-Holder factors
Yeah,
of sin
okay.
k minus 2.
Yeah,
And that's implied by Bremizat.
from the Brahmazan. Okay, okay. Yeah, thank you.
Mhm. Okay, other questions? All right, I'll go on then to the geometric variant. So as I explained before, there are two possible notions of modularity. One is the more classical one in terms of classical modular forms and reductions of Galois representations associated to classical eigenforms over the complex numbers. But you can also define modular forms purely in characteristic P as sections of an appropriate line bundle on the modular curve in characteristic P. And these are equivalent by Riemann-Roch for k at least 2, but for k equal 1, you can have strictly more modular forms in characteristic P than those that arise by reduction from characteristic 0. Because there's an H1 that doesn't vanish, doesn't necessarily vanish. The problem with the classical notion, if you try and formulate the Serre-Waite conjecture using it, is you find that being modular of weight 1 isn't characterized by the local Galois representation. Being modular of weight 1 and level prime to P, and here is always prime to P, implies that the local Galois representation is unramified, but the converse isn't true. On the other hand, if you, if you formulate the conjecture in terms of geometric modularity, namely arising from a modular form of weight k, level prime to P in characteristic P, then the theory does work, the formulation of the conjecture does work well. And you define a geometric minimal weight, I'll call it k geometric of rho, to be k of rho, the original Serre's k of rho, unless the representation is unramified at P, in which case you can hope that rho arises from a mod P modular form of level prime to P and weight 1. And in view of one of the versions of the algebraic formulation, this is equivalent to the minimum value of k at least 1, such that rho has a crystalline lift with Hodge-Tate weights 0 and k minus 1, because it's easy to see that having a crystalline lift with Hodge-Tate weights all 0 is equivalent to being unramified. And so you formulate the geometric Serre-Waite conjecture this way, or you can formulate it this way. Rho is geometrically modular of weight k and level prime to P, meaning that it arises from a mod P modular form of weight k and level prime to P. If and only if the local Galois representation has a crystalline lift with Hodge-Tate weights 0 and k minus 1, now the case k equal 1 being included. And one more observation is that is that this is also equivalent to K being at least the geometric minimal weight and congruent to it mod P minus 1. This is related to the remark that Eknath made. But this phenomenon that if rho is modular of weight K, then it's also modular of weight K plus P minus 1 can also be interpreted in terms of geometric mod P modular forms, because given a modular form of weight K, you can multiply it by the Hasse invariant of weight P minus 1. You can shift the weight by P minus 1. So given an eigenform of weight K, giving rise to a Galois representation, there's also an eigenform of weight K plus P minus 1 giving rise to the same Galois representation. And that's an example of what I'll call geometric weight shifting. The Hasse invariant you can define in terms of the moduli problem that defines the modular curve y1 of n. So you have the universal elliptic curve over y1 of n. Maybe I'm assuming n is at least 3. And then the Verschiebung, the isogeny from E twisted by Frobenius to E, induces a map on differentials from in terms of the bundle, these bundles on y1 of n. It's a map from omega to the p, which you can view as a section of omega to the p minus 1, or as a modular form of weight p minus 1. And its Q expansion is constant, so you can multiply it by it without changing the Hecke eigenvalues. So multiplication by the Hasse invariant is Hecke equivariant. So that tells you that if rho is geometrically modular of weight K, then it's geometrically modular of weight K plus P minus 1. You can also see this phenomenon in the modular representation theory. The Jordan-Holder factors of sim K minus 2 are contained in the Jordan-Holder factors of sim K plus P minus 3, provided K is at least something, maybe 3. Now maybe you need to go further. I don't remember, but from this point of that modular representation theory doesn't easily capture the fact that being geometrically modular of weight 2 implies geometrically modular of weight P plus 1. But from this point of view, it's easy to see, and this also covers weight 1 implies weight P. There's another useful weight shifting, Katz's theta operator, or QDDQ. The definition is more involved. It involves differentiation. It's essentially a differential operator, which can be defined using the Gauss-Money connection. And I'll come back to this in more generality in the context of Hilbert modular forms. But ultimately, what you get in the classical setting is a map from modular forms of weight K to modular forms of weight K plus P plus 1. So the weight shift is by P plus 1. And it's nearly Hecke equivariant. It twists the action of the Hecke operator so that well, it amounts to twisting the corresponding Galois representation by the cyclotomic character. Although you'll see in the context of Hilbert modular forms, there's a better way to view this twisting. Another important fact about the theta operator is that while the weight shift is by P plus 1, if the weight is divisible by P, then the image of theta of F is divisible by the Hasse invariant, and therefore actually comes from, rather than weight K plus P plus 1, it comes from like K plus 2, there being a drop in what people sometimes call the filtration. The filtration meaning the least, the smallest weight in which the, say the system of Hecke eigenvalues or the modular form with that Q expansion appears, or the least or the weight in which you can no longer divide by the Hasse invariant. So this theta operator shifts the weight by P plus 1, and when you iterate it P times, well, it's essentially cyclic with period P minus 1, but theta to the P minus 1 is not exactly the O. This isn't quite correct the way I've written it. Theta to the P is equal to theta times a power of the Hasse invariant, is what I should have said here. But this formula is correct on the level of Q expansions. And you see it, okay, so I haven't written it explicitly here, but Q ddq, if you think about what that does to Q expansions, it sends Q to the N to N Q to the N. So you're seeing the twisting of Hecke eigenvalues in that formula. And you're also seeing that when you iterate it P minus 1 times by Fermat's little theorem, you get what you started with, except at the indices divisible by P. But theta to the P is equal to theta, again, on the level of Q expansions. I should really have said theta to the P is equal to theta times H to the P plus 1, I think. And then in terms of corresponding Galois representations, as I said, the effect on Hecke eigenvalues has this twist, which in terms of the corresponding Galois representations, you can interpret in this way. If rho is geometrically modular of weight K, then its twist by the cyclotomic character is geometrically modular of weight K plus P plus 1. And in fact, you can do better if P divides K. There's a drop in this filtration, and the Galois representation actually comes from weight K plus 2. So if you combine this with the fact that you can always twist down to low weight, as I explained in the algebraic setting using Ash-Stevens, for which there's also a purely geometric proof given by Erikshoven. Then just an elementary analysis of the possible theta cycles, if you just look at the smallest weight in which the twists of rho can arise, then the proof of the geometric version of the weight part of Serre's conjecture reduces to the case of small weight being between 1 and P. So now you have to include the case of weight 1, and then you can complete the argument again using the companion forms theorem, except now you need a companion forms theorem that covers weight 1. So that will bring you down from weight P to weight 1. Okay, so now I'm going to move on to the Hilbert modular setting, the setting of a totally real field, GL2 of a totally real field. which I'll call F. And I'll describe some setup that will be common to both versions of both versions of Serre-Waite conjectures that I'll explain. So firstly, the algebraic today may be spilling over into tomorrow, and then the geometric Serre-Waite conjecture. Okay, so F will be my totally real field. I'm going to assume the degree is bigger than 1. I'm assuming F is not Q, so that I don't, some things, well, I've already covered the case of F equal Q, and some things would become more complicated because of the role played by the cusps. So I'm going to assume, for now at least, that D is bigger than 1. And OF will be the ring of integers. I'm going to fix embeddings of an algebraic closure Q in the complex and in QP bar. I'll let sigma be the set of embeddings of F into QP bar, which, since I'm also fixing an embedding of Q bar into QP bar, so this is the set of embeddings of F into QP bar, which I can decompose according to the corresponding prime over P. And then we can define the Hilbert modular variety for any open common. So now I need to work adelically to have good Hecke theory. So for any open compact subgroup of the finite, of GL2 of the finite Adels, we have a Hilbert modular variety. So this is the Shimura varieties. These will be Shimura varieties for the group restriction of scalars from F to Q of GL2 is what I'll always be working with. So the non-PEL Shimura variety, so maybe people call this EL Shimura variety. And I'll use a standard notation U1 of n and U of n for, so I haven't written it down, but so U1 of n will be the matrices that are whose the entries in the lower row being which is 0 and 1, modulo the ideal here, n is an ideal of OF, and Y of n for principal level n. And you can think of the Hilbert modular variety as a coarse moduli space for Hilbert Blumenthal abelian varieties. So these are abelian varieties with an action of OF and with additional structure, with additional level structure. There's a missing word here, small. So these are D-dimensional, where D is the degree of the totally real field. And if the open compact is sufficiently small, then this is actually smooth. These can be viewed as varieties over Q. They have canonical models over the rationals, and they come with an action on the inverse system of GL2 of the finite Adels of F. The morphisms all being defined over Q. And this is not connected. The components are in bijection for I should have said, well, for Y1 of n. They're in bijection with this class group of F. And more generally, they'll be in bijection with ray class groups. So you can describe them by class field. Okay, so then you can define Hilbert modular forms as sections of line bundles on the Hilbert modular variety. And so Hilbert modular forms of weight K, I'm not going to write down the automorphy factor, but Hilbert modular forms of weight K, and I'm going to include another parameter M here. Where K theta plus 2N theta will need to be independent, at least for now, of the embedding theta. So here, theta is running through the set of embeddings sigma. So this implies that that the K thetas all have the same pair theory, this wonderful word Parisius. And then you can associate an automorphic line bundle on the Hilbert modular variety. And define the space of Hilbert modular forms of weight K M and level U. So notice that K determines M up to a shift in W, since this needs to be independent of theta. And I may have assumed here that U1 of N is sufficiently small, so N is sufficiently small as an ideal. So we have the space of Hilbert modular forms, which of course can be thought of as functions on d copies of the upper half plane, satisfying some automorphy property. But in fact, since we want to work adelically, these will be C tuples of such functions where C is the strict class number of them. I meant here to write that. What happens when you make last minute changes? So this is supposed to be Y sub U. This was meant to be for arbitrary level U. And then specifically level N will be the space of Hilbert modular forms of level U1 of N. Okay, so this should be Y sub U here. And this should also be Y sub U in fact. And there's a natural Heck action coming from the action of GL2 of the finite Adels on the system of Hilbert modular varieties, and there's also an action on the bundles. So TV will be the usual Heck operator, and SV will be the Heck operator associated to the scalar double coset given by a uniformizer at the prime V. And then one can associate Galois representations to Hilbert modular forms. So this is the work of many people. So the existence of the Galois representation is Deline, Cariol, Oda, Rogowski, Tunnel, Taylor, Lazius, Rogowski, Jarvis. So there's but I'm also here stating local global compatibility results, including I'll be stating local global compatibility results at P. So Saito, I think. Okay, let me stay put here. So suppose you have a Hilbert modular eigenform of weight K and level N with eigenvalues I'll call AV and DV. Then there's a unique semi-simple, I'm allowing Eisenstein series here. So It'll be irreducible if and only if F is a cusp form. But stated in this generality, you have an associated Galois representation for any eigenform. And the characteristic polynomial of Frobenius is given in the usual way in terms of the Hecke eigenvalues. For all V, not dividing P or the level. And then at P, you also have local global compatibility, provided all the weights are at least 2. I believe this is open, I guess it's known for parallel weight 1. But then for partial weight 1, I believe this is open. But the local global compatibility, this is a weak version of the local global compatibility. States, but suffices for what I'll be talking about, states that if all the weights are at least 2, then at all the primes over P, the local Galois representation is de Rham, and in fact crystalline if and only if P doesn't divide N. The level is not divisible by this prime V over P. And you can say what the Hodge-Tate weights are. Except it's a little more complicated than the classical setting, because now I need to tell you, now I need to talk about labeled Hodge-Tate weights. So you can divide up the Hodge-Tate weights according to the embeddings. So for each theta in sigma V, you can associate 2 being the dimension of the representation, Hodge-Tate weights, not necessarily, well, I assume K theta, I assume K is at least 2, so that is thing. But the definition is here. So they are the degrees in which the graded pieces of the Dieudonné module, in this case, you can use Hodge-Tate, Hodge-Tate, the degrees in which they don't. Degrees in which they're non-zero. And maybe there's a sign. So these are the negatives of the non-zero. Non-zero degrees for the Hodge-Tate. So, what's being used here is that this is actually free over over FV tensor QP bar, and so you can decompose the Dieudonné module according to the embeddings. And so for each component, you get a pair of Hodge-Tate weights. And then the Fontaine-Mézières-Langlands conjecture predicts that all totally odd, irreducible geometric Galois representations arise this way. They're isomorphic to some rho F or a Hilbert modular eigenform. And I haven't said what geometric is. Geometric means that it's unramified at all but finitely many primes, and at the primes dividing P, it is de Rham. And then this naturally leads to a weak version of Serre's conjecture, which states that every, whoops, I don't need the word geometric there. A little too much cutting and pasting. Every totally odd, irreducible mod P representation is isomorphic to the reduction of such a Galois representation. So for a mod P representation, define geometric to be backwards. And then you can ask, well, what about a refined version of Serre's conjecture? Can you predict the level, some kind of minimal level, some kind of minimal weight? And as far as the level, it should be the prime to P part of the Artin conductor. And this is known that you can achieve this at least under some Taylor-Miles hypotheses, because the arguments that I think the most general results make use of automorphic lifting theorems. But I'm not going to talk about the level, I'm going to talk about the weight. So what can you say about K? Well, again, you would expect this to be determined in the spirit of mod P Langlands and local global compatibility. If you believe that K has something to do with local behavior at P of the corresponding mod P, of some corresponding mod P automorphic representation, then it should be related to the local behavior of the Galois representation at primes dividing P. But when you try to generalize the weight part of Sayre's conjecture, there are two immediate issues you notice. One is that not every mod P Galois representation can arise from the Hilbert modular form of level prime to P, because you have this condition on, there's an obstruction, you have a condition on the determinant. The restriction to inertia groups has to be chi to the W minus 1, where here chi is the cyclotomic character again. This should hold at all primes dividing P. So there are two issues here. You need the W to be the same at different primes dividing P. And if the completion FV is bigger than QP, then this is a non-trivial condition on the local Galois representation, because you have more, so the image of inertia in the abelianization is bigger. You have more possible determinants than powers of the cyclotomic character. And you'll see examples later. Another issue is that there's no obvious notion of minimality, since now we only have a partial order we're working with D tuples of integers. So I've been discussing, there are two versions, two ways to deal with this. One is the more algebraic, to make sense of the notion of modularity of weight sigma, where now sigma will be an irreducible mod P representation of GL2 of OF mod P, or equivalently OF mod the product of the primes over P. And then you want to describe the set of all possible weights from which rho can arise in this sense. And you want to describe it in terms of the local behavior of P, the restriction to inertia at the primes over P. And in some sense, this problem factors over the primes dividing P, so I will soon assume that there's just one prime over P, to simplify matters. And then in the last two lectures, I'll be talking about a geometric version where instead of modularity of, instead of Sayre weights in this sense of irreducible mod P representations of this group, instead of modular representation theory, it'll be more geometric. We'll use the Katz's notion of mod P modular forms, in this case, mod P Hilbert modular forms, and consider the problem of how to predict the weights of mod P Hilbert modular forms from which rho can arise, again, in terms of the local Galois representation. Okay, so now for the algebraic version of the Sayre weight conjecture, as I said, for simplicity, I'm going to assume that's a unique prime over P. Everything works more generally, you just essentially take products of things, take direct products of things over the primes dividing P. And I'm gonna let little k be the residue field, f will be the residue degree, e will be the ramification degree, k0 will be the maximal unramified subextension, and since I'm assuming there's a unique prime over p, d is e times f. And I'm going to write sigma 0 for the set of embeddings of the maximal unramified subextension, or equivalently of the residue field into fp bar. And I'm going to label them tau 0 through tau f minus 1, where you get each from the preceding by composing with Frobenius. So there's a 0 missing here. That should be tau 0. So that's f. There are f of these. There are EF embeddings of k, and you can arbitrarily choose an ordering of the extensions of each of the tau's. So we have EF embeddings here, which I'll label as theta ij. And recall from Eknath's talk that the mod p representations of GL2 of the finite field are just tensor products over the embeddings of twists of small symmetric powers, the power being between 0 and p minus 1. I'm going to allow the mi's to be arbitrary so that they can be negative when convenient, but they only matter, in fact, the mi's only matter in this sense. So this completely describes when two such representations are equivalent. The n's have to match, and the products of powers of the determinant have to match as characters, which amounts to this congruence. So these are going to be the possible Serre weights. And then we're going to try and predict, well, first of all, we have to say what it means for rho to be modular of such a weight sigma mn. So one way to proceed to try and make sense of this notion of modularity of weight sigma would be to work on the Hilbert modular variety that I already introduced and take locally constant sheaves on the Hilbert modular variety. But there's a complication that the interesting degree is the middle degree, which is the dimension d of the Hilbert modular variety, and that introduces complications like the presence of torsion. So what we'll do is transfer to, from that perspective, a simpler setting or a setting that's easier to deal with using Jacquet-Langland. So in characteristic 0, the modularity is seen in terms of automorphic forms on groups associated to, or unit groups of quaternion algebras over F. And I'll take a quaternion algebra like in Stefano's text that's ramified at exactly, that should be unramified. F is unramified at exactly one infinite place. And it should be unramified at P so that the group structure at P is preserved, and we'll be able to see the local behavior. So D completed at P will be GL2 of F completed at P. D P cross will be GL2 of F. And then we have a Shimura curve. And I'm going to assume that the level here, U, is sufficiently small, but prime to P. So that UP is a maximal compact. So isomorphic to GL2 of OFP. Or ODP for a maximal order. OD. And I should comment that for what I'm saying, you could just as well work with a totally definite quaternion algebra and zero-dimensional Shimura varieties closely related to the ones in Christoph's time. And then you can define a locally constant sheaf of FP bar vector spaces on the Shimura curve. You find a local system and associated to each representation sigma. And you have an action of the Hecke algebra on the cohomology. So so the action of the Hecke algebra is on this space. The cohomology of the Shimura curve with coefficients in this sheaf. And then I'll say that rho is modular of weight sigma. So this will depend on the level U and on the quaternion algebra D. If the maximal ideal associated to rho is in the support of the cohomology, where the maximal ideal is, I think this was also defined in Christoph's talk, TV minus the trace and norm times S minus the determinant. And you can, then there's flexibility in being able to drop finitely many V's from the set of generators for that algebra. Doesn't change anything. Okay, so so for the maximal ideal to be in the support means the localization is non-trivial, which is so you can apply Hochschild-Serre spectral sequence here to reinterpret this as the representation sigma appearing in the cohomology with constant coefficients at level U intersect U of P. So go to full level P, and then you have a natural action of GL2 of K on the cover. I'm assuming U is small enough that the cover, the projection here, has this Galois group. So there are no intervening units that would make this smaller. And then you have an action of GL2 of K on this space. And you have a natural map from, which way does it go? From the cohomology here, when you pull back, this sheaf sigma, when you pull back to level P, becomes trivial. So you can, or the sheaf F sigma becomes trivial. There's a hidden duality here. So you just get the invariance up to some cohomology, which so the obstructions to this being an isomorphism are somehow easily analyzed and seen to be Eisenstein, so that maximal ideals associated to irreducible Galois representations can't appear in their support. So you can think of this condition as being that the representation that we're interested in appears in the cohomology at level P in the piece associated to our representation rho. And also, since all these spaces are finite dimensional and the rings are Artinian, this M rho being in the support is equivalent to the system of eigenvalues appearing. So the kernel of M rho being non-trivial. And in fact, one advantage to thinking about things in terms of the Shimura curve is that the Galois representation, rho itself, actually appears here. So this space here is in fact just a sum of copies of rho. But the notion of modularity just depends on the presence of a system of Hecke eigenvalues. So as I said, we could just as well work with zero-dimensional Shimura varieties associated to definite quaternion algebras. And then we can define the set of Serre weights for which rho is modular. So this is of some level prime to P, but with respect, so this in a very weak way depends on the quaternion algebra. Well, a priori, it's not clear at all that it should be independent of the quaternion algebra, but it comes out of the results on, it comes out of Serre weight conjectures that this set will be independent of D, provided D satisfies some compatibility condition with the Galois representation. So again, this is just of some level prime to P. So then this set should depend only on the local behavior as reflected in the restriction to inertia at P. Unless there's an incompatibility between the set of finite Archimedean primes ramified in the quaternion algebra and the representation rho. If rho has no lifts to characteristic zero, for which the associated representation by local Langlands is cuspidal, then this set will be empty. So let's assume we're not in that case. You can also think of it as the set of isomorphism classes appearing in Sokals. So this is making a connection with mod P local Langlands at P. So this, as you saw in Christoph's talk and Stefano's, these limits. So here the V will allow level structure at P. So you'll have an action on this direct limit of GL2 of FP, or D sub P, which is isomorphic to GL2 of FP, because I assume that P was unramified in D. So this limit has an action of the of GL2 of FP, and the representations, the weights, the sigmas that are appearing here are the isomorphism classes appearing in the circle. So this is seeing a little bit, it's detecting something about the conjectural local Langlands correspondent of rho. And it also answers the, if you know what the set is, it also answers the original questions about what weights are possible, and not just what weights are possible, but what sorts of local factors at P are possible. But subject to this restriction that we can only see, we'll only be able to see the K thetas that are at least the weights for which all the K thetas are at least 2. So we'll be missing out on weight 1 or partial weight 1. In the same way that Eichler-Shimura, the Eichler-Shimura setup was missing classical weight 1 for F equal Q. Now we'll be missing not just parallel weight 1, but also partial weight 1. And I see, let me see what's next. Okay, so this is probably a good place to stop.
Okay, thanks, Fred. So, are there any questions or comments?
Yeah, so can you again explain the last remark which you made about the connection with local Langlands correspondence?
Okay, so this limit. So if you run overall open compact V, has an action of GL2 of the finite Adels, or if you like, fix some tame level away from P, sufficiently small, and take the limit over all overall open compacts at P. And that limit then inherits an action of GL2 of FP, or in this setup, D completed at P, which is isomorphic, oh, not D completed at P, DP cross completed at P, which is isomorphic to GL2 of FP. And if you, so in the framework of mod P Langlands correspondences, this representation gotten by a global construction corresponds to the representation rho. So it's local factor, if there is a, if we can factor it, over the places of P, or fix some tame level away from P, then this representation that you get in this way from this global construction, this representation of GL2 of F completed P, GL2 of the local field, should, up to multiplicities, only depend on the restriction of our mod P representation rho to the Galois group of FP. which I'm calling K. And well, there's a question of whether it only depends on the local Galois representation, which is related to what Christoph was talking about. And what can you say about this local? What can you say about this representation, this modular representation of GL2 of FP? And well, one thing you can say about it that comes out from Serre-Waite conjectures is what the representations appearing in its SOCL are. Does that answer your question?
Yeah, thank you.
Any other questions?
Was that second statement actually a theorem now?
Um,
A set of isomorphism classes, that's a fact. The algebraic Serre-Waits that you defined. Or is this a conjecture?
So the statement here is, right, so what I've said here I think is automatically true, but then the Serre-Waite conjecture tells you what this is in terms of the local Galois representation, and that's almost a theorem, yes. And I'll get to that in the next lecture due to G and collaborators, but there are technical conditions on the global Galois representation that satisfy Taylor-Wiles hypothesis.
Okay, if there are no more questions, then let's thank Fred and all the other speakers this afternoon. Thank you. Bye.
Thank you.